The big new idea for today is that an object can actually change its value over time. So in particular, we'll look at lists. Lists can change their contents. The same list can contain different things as time goes on. So I'm going to demonstrate how that works by telling you a story of the history of suits in playing cards. So we think that playing cards were invented in Asia, and they began with 3 suits: the coin, the string, and the myriad. And these were representing different denominations of money, because what are cards good for? Well, of course, gambling. Okay, so those are our suits. And we're going to try to keep track of these original suits by using this assignment statement, and then we're going to tell a story about how those suits changed over time. So playing cards migrated over to Europe through Egypt, we think, and in the process, this myriad suit was lost. And it was also the case that the string suit was lost, leaving only the coin. By the time playing cards reached Spain, there was a need for some new suits. So, in the Spanish deck, you have the suit of cups. You also have the suits of swords and clubs. So the coin, the cup, the sword, and the club, I believe, exist in Spanish decks today. And we've seen so far that you can pop off one element, you can remove an element that might be anywhere in the list. Pop always removes and returns the last element in the list. You can append a single element, or you can extend a list by adding multiple elements in a sequence. The Italians adopted playing cards, of course. And in Italy, the way you say sword, which is element number 2, is you say spada. So we have the spade. And then the French decided to change some of the suits. And so the coin and the cup went away, and they were replaced by the heart and the diamond. So here are the suits that appear in a modern American deck: heart, diamond, spade, and club. I believe they're also used in France. Okay, way up at the beginning, we bound original suits to suits. Let's see what original suits is now. It's the same as suits. And that's interesting, because we bound it way up here, and then we made a bunch of changes. But it turns out these were just 2 different names for the same object. And so changes to one were reflected in the other. This is the first example in this course of an object changing state. So something big just happened right now. The same object can change in value throughout the course of computation. If I bind the name same person to some baby, by the way, this is a Unicode character called baby, then if that baby grows up, same person is still bound to the same person, but changes appear in that object. If I bind 2 different names to the same object and that object changes, well, those changes will be reflected regardless of which change I use. Okay, so all names that refer to an object are affected by a mutation. Now, becoming an older woman isn't necessarily called a mutation out there in the real world, but in computer science, mutation is a word that's used whenever there's a change to an object. Only objects of mutable types can change in their values, and lists and dictionaries are examples of that we've seen so far. So let's look at how to change the contents of a dictionary. If I create a dictionary called numerals, with I bound to 1 and V bound to 5 and X bound to 10, I can look at the contents of the whole dictionary, or I can look at a value bound to a particular key. I can also change the value bound to a key, at which point if I look it up again, I'll get a different answer. And the numerals dictionary has changed. notice that the binding between x and 10 is just gone completely, and it's been replaced by x paired with 11. Now I can also make new entries to a dictionary just using this element assignment statement. So now numerals has more in it than it used to, and I can look up what L is bound to. I can also get rid of a binding by using the pop method, which takes a key and removes the key value pair for that. So now if I try to get the value for the key x, there's nothing there because numerals has changed. By the way, mutation can happen within a function call. So a function can change the value of any object that's in its scope that's a mutable value. So if I say 4 is 1, 2, 3, 4, and the length of 4 is 4, some mystery function could be called on 4, at which point the length of 4 would be only 2. What sort of mystery function might do that? Here's one. So this one takes in an argument we'll call s and then pops it twice. So invoking the method pop removes the last element. So we define the function, we create the list, we call mystery. Mystery introduces a new frame in which s is bound to the same object that 4 is bound to. So that when I pop that, I'm actually removing the last element, which forever changes the value to which 4 is bound. Now 4 isn't bound to anything different than it was before. It's just that this list is different. It has different contents. Popping again means that it will be even shorter. Here's a different function that would do the same thing. Remove every element after index 2. And that would mean removing the 3 and the 4, and replacing that slice of the list with just no elements at all. Now, what happens when we create 4, and then we call a mystery function that doesn't take any arguments? Does it still have access to 4? Can it change it? Sure. How does it do that? Well, it just refers to the 4 list, which is within its scope. It's in the global frame. Anything can refer to something in the global frame. And so it just starts popping stuff off of 4.